Hello there, Unplucked listeners. Before we get going on this latest episode, I just wanted to give you a quick update. After 43 incredible episodes, we're hitting pause on the podcast for a little while. It's not goodbye forever, just time for a breather, some reflection, and who knows, maybe dreaming up what's next. Before we go, we want to give a heartfelt and feather ruffling huge thank you to our host, Andy Vance. Andy brought his energy, his insight, and his signature style to every single conversation, helping us dig deep into the stories that matter in poultry science. This podcast wouldn't have taken flight without him, and we are truly endlessly grateful. If you've missed any of the episodes along the way, now is the perfect time to catch up on all 43 amazing conversations we've recorded, from groundbreaking research to industry insights to voices shaping the future of science. There's oh so much to revisit, re-listen to, and share. From all of us behind the mic, thank you for tuning in, supporting the Poultry Science Association, and helping us pluck the most fascinating stories from the field. And now, here's today's episode, a cool look into PAA's shelf life in the chiller.
What we're finding is that we can actually stabilize PAA 8 to 10 times longer than normal using these additives, while not sacrificing its efficacy and antimicrobial properties.
One way or another, a visual representation of, that's the first thing I'm looking at. Do I want to eat that chicken? Do I not want to eat that chicken? It might be perfectly safe, but if it doesn't look right, I'm not going to buy it.
Welcome to Unplucked, the official podcast of the Poultry Science Association. This is the podcast where we strip away the fluff and get real about poultry science from bench to barn. I'm your host, Andy Vance, Executive Director of the Poultry Science Association. You know, as temperatures drop, we're diving into the cold, complex world of poultry processing with Georgia Tech researchers Daniel Sabo and Stephanie Richter from Georgia Tech Research Institute's Intelligent Sustainable Technologies Division. Their focus is on peracetic acid, PAA, a vital antimicrobial in poultry chillers, and specifically how it breaks down over time. We're going to talk about some research stemming from an industry concern raised back almost a decade ago now. Back in 2019, processors noticed that PAA was decomposing faster than expected in immersion chillers. And these are large tanks, of course, where poultry is cooled and sanitized. And in those systems, that's a challenging mix of fats, oils, proteins, and minerals that all could potentially interfere with the stability of PAA. With a data-driven approach and a focus on decay kinetics, Dr. Sabo and Stephanie Richter aim to uncover what's really happening inside those systems and why it matters for food safety, compliance, and operational efficiency. All right, friends, let's kick right off. To get us started, I'd wonder if you might walk us through the specific stage of poultry processing we're discussing and why this particular situation was such an important topic for us to research and understand.
Right. So this is the stage where it's our last step of intervention in primary processing. This is where, after you've done all of your evisceration, you removed all of the internal organs, and you have to chill the bird down to 40 degrees within 4 hours. And this is where they add their antimicrobials, or PAA, in an effort to control contamination and ensure food safety. Antimicrobials that they've used most recently since about 2019, 2018 has been peracetic acid, or PAA, in an effort to control those microbial growth and food safety concerns.
Yeah, I'd like to build on that. So the reason this project came to be, Andy, is because we got invited to similar like a closed door ceremony that was held by the National Chicken Council. And it was really this talk about industry, and they're talking about what's going on with my PAA, because there's sound research there. We know what PAA does. It can kill salmonella. We know it can kill Campylobacter, but there's other factors like you mentioned. There's these fats, these oils, these greases. There's other components in these large chillers that also have an impact on peracetic acid, its activity, and its ability to kill off these foodborne pathogens of concern. So that's where it kind of got me and Dan were like, let's help the industry. Let's do this further research, take it a step back, do some applied research. What components are happening in the chiller and what is their compounding effect on the stability and efficiency of PAA?
And one of the biggest questions that came out of that council was a lot of different concentrations of PAA within their chiller. The concentration ranges swings greatly throughout the processing day. that they are shooting for, say, 80 parts per million in their main chiller, and sometimes they'll see 40, and other parts of the day they'll see 120, and they don't know why.
Oh, wow.
So what we wanted to do, as Stephanie mentioned, is take that step back and figure out, well, why is it swinging so much? Is it because of how they're adding it, or is it a component impact from all the stuff that's being released from the poultry products in that chiller media, that fats, oils, greases, the protein? Is that having an impact on PA? And then if we know that, we can develop strategies to help control it so that we can stabilize that PA and keep that concentration within certain targeting bounds instead of these big 50 parts per million swings that they've been seeing.
This whole thing, and I want to get into the technical aspects and challenges a little bit later on in the program. But I want to kind of start and go back to that 2019 as you're getting involved in this project, and maybe let's start with how it came to pass that your team in particular starts digging into this. So you're having this conversation with industry and our great partners, the National Chicken Council, and so on. But what about your institute in particular and your department kind of positioned you well to conduct this kind of research, and how this becomes something where the two of you are all of a sudden becoming experts in decay kinetics of PAA?
So, Dan, I'll start us on this because it really started when I came on to do my master's thesis research. And I was working with Comus Haynes, who was looking at alternative chilling. So, basically, using ice slurry as an alternative chilling medium in the chiller. And it was kind of the same time where we shifted from the chlorine focus as using that as our antimicrobial, moving to peracetic acid. So, Dan's a chemist. I'm an applied microbiologist. So we had to source some PAA. We had to figure out what kind of blends, what's the concentration of acetic acid to hydrogen peroxide that industry is using. And because there's a little bit of a displacement factor within your liquid medium, because obviously the peracetic acid can't penetrate into the ice particles of ice slurry. And are we compounding it, or is the temperature affecting the stability? So we were kind of already like going through the motions of like what's going on with this peracetic acid as we're trying to come up to speed with using peracetic acid for antimicrobial studies to prove the efficacy. So basically, everything that we learned trying to use ice slurry as an alternative chilling media in a chiller
Mm-hmm.
kind of helped build up our questions that we ourselves wanted to answer about peracetic acid.
And then so we started what's called an exploratory project with the Agricultural Technology Research Program, or ATRP, that we have within our division here. And it's a state of Georgia funded program that GTRI has.
Led by Doug Britton, that all of our listeners should
Yes,
know.
very much so. Great friend of the program, as we say in the radio broadcast business, longtime friend of the program.
Right. And so we started an exploratory project to answer some of those questions that Stephanie was running into with her ice slurry project and her master's thesis on PAA and its impact. Does the concentration increase because you're using slurry because it can't penetrate into the ice component? It's concentrating into the water, the liquid portion, and does that impact its overall efficacy? So we started an exploratory project to start answering some of those basic questions. Well, what is PAA? How does it work as an antimicrobial? Learning all we can, as much as we can, and become almost like a subject matter expert in this area. And then that kind of like launched us into our advisory committee, where we have people from the industry come in, learn about our projects, and they learn that we are becoming known in this area for PAA. And that kind of started the conversation where they started coming to us with problems like, oh, we have these big swings in PAA within our chillers. Can you help us figure out what's going on?
Uh-huh.
And that kind of just launched us into our multi-year project where we're trying to answer those questions for the industry so that they can have as much information and can apply it within their processing plants.
And I think it's a great example. But we talk about interdisciplinary or even transdisciplinary research quite a lot in academia and working across departments and so on. Your whole program, I love, I think is a great model for doing that well, because you've got a building full of, oh, this person's an engineer, this person's a robotics expert, this person's an expert in microbiology, and so on. Great example. But the other piece of this that I think is really part of the reason we wanted to talk about this with you is understanding the relationship between industry and academia, and the way that we can here's a great example. Stephanie, you described it well. Industry is facing this issue out in the field, in the real world, so to speak. We take this to an academic setting and say, hey, help us understand what in the heavens is going on out here. You take it back to the bench here and look under the hood a little bit. And then we come up with an applied solution, like from industry to the bench and some basic science, back to applied science, back to industry again. What a great story. And I love those kind of public-private partnerships that really drive the science forward. Let's set the stage a little bit here in terms of scope of the problem or potential industry impact. When we talk about peracetic acid specifically, and Stephanie, you kind of set this up, that we were moving away from chlorine to PAA as maybe our key antimicrobial here in the facility. What is it about PAA that makes it such a critical tool in the toolbox for processing and food safety, particularly in the chiller scenario? And how big a piece of the pie, so to speak, does it occupy as a tool in the toolbox for these applications today?
The thing about peracetic acid, it's a great antimicrobial. It's wide efficacy in controlling bacteria, fungi, spores, and protozoa, those kind of things that cause food safety issues. And it's really effective against bacteria, which is of interest to the poultry industry. And the thing about PA is that when it breaks down, it does so into innocuous or unharmful components. It breaks down into acetic acid and water. And the use of peracetic acid as an antimicrobial allows you to keep your organic label. And you talk about how big of a piece of the pie it is. Well, it's used throughout the processing plant, not only in primary processing, also in secondary processing. They are now utilizing it in inside outside bird washes. They use it in the chillers, both pre, main, and finishing chillers. And they'll use it in parts dips later on, and then even parts chillers, depending on the processing plant. But it's used pretty much throughout the plant as a antimicrobial agent, just because of its wide-ranging efficacy and antimicrobial properties.
It's even used in cleanup. So if we build on that, PAA is used throughout the whole plant throughout the whole day. Outside of your actual processing shifts, PAA can be applied during cleanup shifts as well. It's all about the cocktail you have of it. Your percentage acetic acid, your percentage of hydrogen peroxide. Like higher hydrogen peroxide concentrations are really for cleanup.
Sure.
When you're really trying to wash down the whole plant, you definitely use a much lower concentration when it's in the actual chiller because there's a relationship with the bleaching impact on your product, right? Like you don't want a white product. People are not going to buy that product.
Which I think is a good segue into the complexity of managing your chiller, right? That's a complex environment that we're dealing with. Fats, oils, proteins, minerals, PAA, the concentration of the mix. As you started digging into this problem and starting to gather some data, what did we learn about the way those components in the chiller interact with peracetic acid? And as you started to try to map throughout the course of you mentioned the concentrations, but what did we learn as we started gathering data?
We started originally mapping out the chillers to see how those concentrations of all those components within the chillers change throughout a typical day. So that way, when we go back to the lab and do the benchtop testing, we're using concentrations of the fats, oils, greases that were typical of a processing immersion chiller. And so using that information, then we went step by step looking at your total suspended solids, total dissolved solids, your fats, oils, and greases, component by component, and its impact on PA stability and how fast it breaks down. And what we found is that pH above 8.5 causes PA to rapidly break down. We found that TSS does have a minor impact on PA stability, that TDS or total dissolved solids has the highest impact on stability. And we saw that temperature also impacts PA stability. Higher the temperature, the less stable it becomes. Colder the water, it actually helps stabilize PA. And we found that formulation of the PA itself can actually impact its overall stability within these chillers. As Stephanie mentioned, that they come in different concentrations of peracetic acid and hydrogen peroxide. If the hydrogen peroxide level is high, you don't want that in the chiller, but it actually helps stabilize it and keeps it around a lot longer than the targeted 5 to 10% peroxide levels that are typically used in the immersion chillers. And going back to that total dissolved solids, that's an umbrella term. It actually includes proteins, blood, the minerals or cations that you had mentioned. And we wanted to see, well, which one of those has the highest impact on PAA? So we went component by component in that case, because as any good scientist starts, we looked at literature to see what work had been done so we don't replicate anything.
Mm-hmm.
And we found in literature that certain things had the impact on peracetic acid's stability, and proteins was one of the things that was cited to have a huge impact that it causes to rapidly break down. When we did it, when we used poultry relevant proteins, we found that it actually did not have an impact on PA alone. So we looked at 3 different proteins. We looked at lipids or fats. We looked at poultry blood and then cations. And individually, they all had a minor impact on stability of PAA. It wasn't until you started combining them together, like your blood and your proteins together, then you started seeing a massive impact on PAA stability. And what we kind of think is going on there is that when PAA is shipped out to the processing plants, it includes a stabilizer agent so that you extend out its shelf life. So you can store it for a while before you have to use it in the plant. And the stabilizing agent also kind of protects the PAA within the chiller media. It acts as almost like a bodyguard. And what happens is when you start combining these components, you're overwhelming that bodyguard and allowing the other components to get easy access to PA and cause it to break down a little bit faster. And so what we found is that when we start doubling up or tripling up of those components, that's why the overall TDS, when we just tested the umbrella component, it had a massive impact on PA stability.
And I'll put a plug in here. Dan kind of briefly mentions it. Like, we went and tested at the plant throughout the day. Like, we went to multiple plants and we stayed there through the entire portion of processing. So 15-hour days characterizing pre-chiller and main chiller. And as we all know, each processing plant has a different setup. So it was really important for us to go through the different types of plants that have maybe a different order and different concentrations, because everybody has their secret sauce. Everybody has what to them gives them the best reductions or like completely eliminates their salmonella and their campylobacter. So we sampled throughout the entire day, made sure that we covered startup to the last bird. Like, we were just basically chasing the last bird, similar like the cleanup crew does. And we characterize on so many different parameters: fats, oil, and greases, COD, TKN, TSS, TDS. All of that characterization also took place. And it was really interesting because, like, the first 2 hours is really where you see the most change within the water structure. But then, because of Dan introducing, like, how there is a stabilizer component because of PAA's reactivity with itself even, that you do start to reach, like, a steady state. You reach this equilibrium basically once the clean matrix has, like, established itself. Then it's pretty stable throughout the day, which was so surprising to us because we were expecting it to be look like, your heartbeat when you're thinking about something stressful all over the place. But no, this thing was like, like calm water.
When you're looking at all of that data, all those different data points, the different concentrations of the different pieces of the mix in that chiller that you're talking about, walk us through, for the stats or methodology nerds who are listening, what kind of testing and modeling we're using to really study the decay kinetics here as you start to put all those pieces together. What was the approach there of how we modeled that out and tested it?
So there was a couple approaches we could have used. We could have just looked at the concentration of PAA change over time in these different conditions, but we found that that wasn't the best way to look at the data. So we actually started using PAA's half-life, or the time it takes for half of the concentration of PAA to disappear.
Mhm.
And that kind of gave us an apples to apples comparison to under different conditions. Doesn't matter what kind of starting concentration you use. And so we utilize just a typical half life formula in which we have our starting concentration, a concentration of PA after time, and then you put that into your decay formula and you'll get out a half life. And so everything we compare for our decay kinetics is just all in PA half lives. So we'll report a typical half life of PA in just pH 9 adjusted water. And it has a typical half life of anywhere between 120 minutes to 200 minutes. And so that means it takes 120 to 200 minutes for half that concentration to disappear. And then depending on what kind of condition we're looking at, we can see, well, does it do better than that? Like stabilizes it out, like with the cold water, where we can actually extend it out to about 300 minutes. Or if you put it in TDS, you're down to 5 minutes. So you can actually utilize that to look at the massive impact on PA stability, where it's all happy chugging along at 120-minute half life, and then you introduce it to this TDS, and you're now down to 5 minutes. And we actually had to adjust some of our collection methods in order to catch the decay, because there was times that we would run the test and we wouldn't see it, and we're like, what happened? It decayed so much faster than we were expecting. And so we just had to change up our collection methodology in that case because it was just so much faster than we were expecting.
And Dan, I'd like to put a plug here for the listeners because we just gave so many acronyms and so many numbers with benefits and cutting things. So the great thing that this this project has had is that we're doing this to support some industry concerns or questions that we've received, right? And ATRP is all about supporting the industry however we can. So, what we've taken and consolidated with Dan's project that he's led with PAA is now we're releasing research briefs. So, small bulletins of consolidated data of our big takeaways of what we found. And I think another great part of what ATRP provides is we do a lot of applied research, right? So we're not just staying on the benchtop. We're doing all of our testing in the plant, or we're going to get samples from the plant and bringing it back to the lab. So it really is representative of what the plants are seeing. So if you want to watch, we've got a couple research briefs out, and a lot of our titles are like, "Who killed the PAA?" Because that's the main question: is what's going on with it. But if our listeners wanna, like, see more about our research briefs, that's at atrp.gotech.edu under publications.
Yeah, and we'll actually include links to some of those in the show notes of this episode. So wherever you're listening, your favorite podcast, just to access the show notes, and we'll include a couple of those links because it's really fascinating. And I chuckled when you mentioned all of the acronyms. I've said for years, agriculture's run on TLAs, three letter acronyms. Sometimes we have four letter acronyms, but the importance of this research. We started talking about earlier how ubiquitous in the processing facility PAA is. So I want to start thinking about the importance of understanding its decomposition for processors in a couple different venues. And let's start from that food safety and regulatory standpoint. Obviously, we know Salmonella, Campylobacter pathogens of prime importance for us to control from a food safety standpoint. But walk us through the importance, as you saw it when you were undertaking this and continuing to work in this area of understanding the decomposition of the acid from that food safety and regulatory aspect.
So what's so interesting about PAA is, like, you can only assume what your concentration is. And I will say one of the things that we ourselves have encountered is it's not that it also reacts so quickly, Andy. The other issue here is how do you quantify it? So in the plant, typically people are using titration kits. So just like my first job is I was a lifeguard
Mhm.
and I was doing little pH kits to make sure that kids were safe, that we weren't completely consuming all of the chlorine in the pool. It's a similar thing of like the PAA and the chillers. Like, how do we know it's actually there? How do we know what concentration is? And the go to in a lot of plants is using a titration kit. And that's counting drop by drop. Sometimes up to like 100 drops, and there's 4 different steps typically. So there's some human error in there. There's some like drop efficiencies depending on how you angle the bottle, if it's straight up or if it's at an incline. Like you could have size differences. So a lot of that is an issue. It's a problem. It's a concern. What me and Dan, we like our little DPD meters, which is like a calorimetric version of it. Dan, what does DPD stand for? Give me that acronym.
Oh, I don't know.
I love playing Stump the
I'll
Scientist. We never get to do this on the show. And
yeah,
like you usually as the layman in the room. I love it. This is so great.
yeah, yeah. It's a long chemical name. It's actually used to measure chlorine back in the day, but we've co-opted it for PAA. And just build off what Stephanie was saying is that we don't measure PA directly. What we do is it's so reactive, and you have to react it with an intermediate chemical. In the titration kit that Stephanie was talking about, we actually react it with iodine and then use a starch indicator to determine its endpoint or the concentration of PA. In the DBD method, the colorimetric is we're reacting it with a chemical, DBD for short. I'll have to look up the name here in a minute. But it's a chemical that actually turns magenta when it's oxidized. And so the PA oxidizes it, turns this color, and from that color, we can get a concentration of PA to back calculate. And then there's other methods where you can use electrochemical, but again, it's reacting with a electrode in order to give you your concentration. It's generating a voltage change, and that's what you're measuring. So you're not actually ever measuring PAA itself. You're measuring an intermediate chemical and assuming the conversion is correct.
So we start figuring all of this out, right? So you're figuring out, okay, how do we understand the decomposition, this decomposition kinetics, which is a term I hadn't heard of before today. Love that. You Stephanie, this is so funny. Stephanie looks up the name, and there is not a chance in South Florida in July that I'm going to be able to pronounce
Andy, I
that.
want you to
It
say
is
it.
not going to happen. There are so many letters in those words.
I think I can do it. It's N-diethyl P-phenylalanine diamine.
I feel infinitely better about my high school chemistry grades now by watching the two of you attempt to pronounce this chemical that you're using on a daily basis in this research trial. My heart is full.
N-diethyl P-phenylalanine diamine.
There you go.
But yeah, so that's why in this case we say DPD.
DVD. All right. Now, so we start understanding how this works, like the decomposition of this and the half-life, to kind of go back to that. We've talked about, obviously, it's super important for processors to keep salmonella and Campi in check. We know that it's ubiquitous in the plant as a tool. We want to protect the efficacy of it. And we see we have these ebbs and flows throughout the course of the day. And as you start getting that data that we talked about earlier, understanding which concentrations of which agents in tandem in the chiller start affecting the concentrations and efficacy of the product, how does that help the processor either improve operational efficiency, reduce their costs? Like, are there opportunities there for them to be able to better manage the costs associated with keeping, I'll just say, for lack of a better term, enough PAA in the tank to make it work? What do we start figuring out there in terms of some of those practical implications?
Right. So in the example of pH, if we allow our chillers to get above a pH 8.5, it's going to cause PA to decompose rapidly. So its concentration is going to be lower than what you expect. So by providing that information, processors can choose to drop their pH to below 8.5 or maintain it between 7 and 8 in order to get the best efficacy of PAA and the best concentration of PAA around. By providing them with information about the fact that it's TDS, maybe they can put some type of filter system in to remove some of that TDS in their recycle water or their reuse water. And that way, if you're reducing the amount of TDS present, we keep PAA around longer as well. So using this information, we can then start suggesting strategies or suggestions on how to keep PA around longer in their chiller. And that's kind of where the project is leading now, is what chemical additives or physical additives can we do within the chiller to help stabilize PA and keep it at concentrations that we're trying to target within those chillers. And so that's what we're trying to do, is provide as much information to the processor so they can make informed decisions within their plants.
As you think about promising solutions or changes in practices, you alluded to some of those now, filtration and some of the other things, but what have we seen so far in terms of either solutions or changes that have already kind of come from the work? And then pull out your crystal ball and tell me where you think, like, hey, here's some things we're really excited about that might come from this research in terms of solutions or changes in practices in the plant.
Right. So one of the biggest examples is that we were helping a processor with some of their PAA and doing some testing with them and found out that their chemical supplier was giving them a PA that was too high in concentration of peroxide. And through our testing and our decay studies, we helped them to notice that and to correct that by changing the vendor. Just because you don't want, as Stephanie mentioned earlier in the show, if you have too high of peroxide, it's going to start polluting your product. It's actually going to start, even if your concentrations of peroxide and PA are too high, you're going to get wingtip burn, that kind of like a blacking of that. So by providing that information, they were able to make an informed decision to change out the vendors for a product that had tighter control over the peroxide levels. And then as far as where we're kind of excited to go is I kind of mentioned it already, is that, well, what kind of additives can we put in with our PAA to kind of help stabilize it in those conditions? We have a student right now that's kind of helping to kind of figure that out. If we look at adding additional stabilizing agent or other chemicals that are typically used in the food industry already, and if we stay within labeling requirements, can we add it to the chiller and help PA stabilize a little bit longer? And what we're finding is that we can actually stabilize PA 8 to 10 times longer than normal under these conditions using these additives. And so we're just trying to figure out what those concentration targets are, getting enough replicates so that we have some sound statistics to say, hey, if you add this amount of extra stabilizing agent, you will extend out your PA a lot longer and you reduce the overall cost of your PA well, not sacrificing its efficacy and antimicrobial properties.
Yeah, Dan actually had Courtney Martin. She's one of our co-op students, presented at 2025's PSA conference. And I think she actually won an award for her presentation, which was on extending the half-life of PAA through And very, very small concentrations of additive are we even looking at here, and seeing such a benefit and keeping the PAA stability, because this all loops back to food. There are very strict food safety standards out there, and we always want to ensure that our consumers are eating a great product. So when Dan loops back and talks about how we had somebody reach out, they were having some PAA concerns
Mm-hmm.
because their chicken didn't look very good. It was whiter than normal,
Yeah.
and we did find, like, chemical concerns because we all know, like, we are all consumers ourselves in one way or another, and a visual representation of whether or not I'm gonna buy that, like, that's the first thing I'm looking at. Do I wanna eat that chicken? Do I not wanna eat that chicken? It
Absolutely.
might be perfectly safe, but if it doesn't look right, I'm not gonna buy it.
You eat with your eyes first. It's known, right? That's why a high-end restaurant chef spends so much time on the plating, and you do eat with your eyes first. That's a really good call out. So, but that's a great example, something I've been thinking about. And I mentioned this at the top of the program. I think GTRI does a really tremendous job of that, working with industry, as many of our academic colleagues do, of partnering with industry and in collaborative efforts like this. I'm wondering if the two of you have any advice or observations, recommendations for your fellow researchers, particularly the university space, about collaborating with processors specifically to apply research in the real world setting. You guys do it very well and have a great example here of a successful project. Any advice or observations you have for colleagues who are trying to do something similar in terms of a collaborative effort with the processing community specifically?
I think where we add and gain so much value through our program or through ATRP is we have an advisor meeting every year. We give project updates, kind of detailing like what we've been doing, what our findings are, and we ask for feedback. We also ask our advisors, who are part of all of the bigger companies and smaller companies and different entities within poultry, what's on the horizon? What issues are you seeing? And I think as long as we keep our research relevant and are able to help issues that are out there, that's how you keep collaboration alive. And that's how you keep industry feeling supported and industry interested. Because we can come up with crazy ideas. It might not be a problem they're even focused on, right? So just want to make sure that the work that you're doing is actually something that industry is having an issue with and needs some research in.
Yep. And talking to the processors or people in the industry, I think is the number one thing. To Stephanie's point, is that we talk to them to feel out where their pain points are, what the problems are, where we can help add value to their process. PA was one of those, is because it costs them a lot of money and they're having issues with keeping it in concentration ranges where they wanted it. And so we developed a project around that. We talked to other processors about other projects that had developed into long-term projects looking at different areas. And so it's just that feedback, that back and forth with the industry. And they like talking to people like us and the academics because they want to be able to answer these questions. They don't have huge R&D budgets, but being able to collaborate and help and talk to them and figure out what their problems are, and if we can add value to them, they love that. They love talking to us and figuring out what we can do to help them. And I think that's the number one thing.
And if you got a crazy idea, because I love having a crazy idea, and if you're looking to see if it's a sound crazy idea, email Juanfra at Wayne Sanderson. He's so responsive, and he's always looking for something kind of crazy out there that is going to fix a big problem. So, like, it doesn't have to be a small thing. It can be out there. It can be extremely outrageous. And if you want to bounce it off somebody, reach out to Juanfra. That's what I do.
He's one of my favorite, what I'll call thought leaders, I think, in our community. I follow him on LinkedIn, and just very uplifting and just is super insightful. We had a great PSA think tank a couple of years ago on salmonella, and it was one of the participants. And I learned so much about how this works in the real world just by talking with him through that project. Great, great, great call out there, Stephanie. Friends, as we wrap up what has been a really fun conversation here, I want to just ask maybe a last question. Could the research and the findings that you've had here, this body of knowledge that you've created now about PAA and the chiller, are there applications to other antimicrobial systems or other aspects of food processing beyond poultry that you'd say, hey, what, there's some applicability here. I hope others in these spaces read some of this literature and pick up on this. What are your thoughts on maybe the broader application of knowledge or transfer of knowledge from this work into other aspects of antimicrobial management or food processing?
So we actually have been talking to a meat microbiologist out in Wyoming about PA application within the beef industry. And so we put in a USDA NIFA project, a proposal looking at doing some work with her and the PA within that area, helping to extend out the shelf life of the product. And so it does look like it could fit into other applications such as the beef or the pork industry. So I think that there would be some crossover from the kind of research that we figured out here. They don't use chillers in those cases, but I still think in the spray cabinets or in dips, I think there is some ability there.
And you see, like, the biggest benefit, like, we've got great research, but we've set a great foundation for our experimental setup. You don't know what's going on if you just sample once or twice a day. If you're trying to mimic a system, follow the whole day. Characterize like Dan did on his project. Go for 15 hours and grab a sample every 30 minutes. See what's going on. Like, what are some correlations? What are some relationships? And sample as many things as you can. Characterize as many different components because there's synergies there that you can uncover that are going to have aha moments for your research. Like, that's what my biggest thing is we found so many interesting relationships just by doing the big heavy lift up front and doing that large chiller characterization studies.
That's a great way to end it, and what a fantastic, conversation. I just want to thank both of you, Daniel Sabo, Stephanie Richter with the Georgia Tech Research Institute. Super example of a really collaborative, interdisciplinary approach to solving real-world problems. If you're not engaged with them online, we mentioned we'll include some of the links to some of the material in the show notes of this episode, which was produced by Lindsay Johnston with editing and engineering by Michael Lund of Parasol. Thank you to both of them for making us sound brilliant every week on Unplugged. Friends, if you want to experience some of the great cutting edge research, as Stephanie mentioned, she and their team presented at the 2025 PSA annual meeting in North American Scientific Conference last summer, well, it is not too early for you to start thinking about planning your trip to Toronto, as the 2026 PSA annual meeting and North American Scientific Conference will take place in one of the most beautiful cities in North America. We'll be downtown at the Convention Center this July. If you haven't registered yet, please do so. Think about submitting an abstract or 2 or 10. Love for you to share your research with us there in Toronto. It's going to be one of the biggest weeks of the year for poultry science and helping to advance the discovery, dissemination, and practical application of knowledge in the poultry sciences. For the Poultry Science Association, I'm Andy Vance.